Welcome to the deep dive. Today, we're going to get into something pretty amazing about large language models, LLMs. It's about how they seem to, well, learn new things right in the moment. Have you ever been using one, maybe given it a couple of examples in the prompt, and then it just grasps a new pattern? Something it definitely wasn't, explicitly trained on. It really does feel a bit like magic sometimes. These huge models, their main training is done, but they still seem to be adapting in real time. This is called in-context learning, or ICL, and it's honestly one of the most fascinating and maybe puzzling things about these AIs.
It really is. Because, in standard machine learning, when we talk about learning, we mean something very specific. It involves changing the model's core structure, those parameters or weights, usually through a big optimization process with lots of data. It's a definite change. But with ICL, that kind of explicit change to the model's stored weights just isn't happening when you're interacting with it. So that sets up the central mystery we want to explore today. How can these LLMs perform new tasks based on just a few examples in a prompt without any of that conventional training?
Right. And our mission here is to unpack some really interesting new research that puts forward a pretty compelling explanation. This paper suggests it's not just a fluke, but maybe a hidden mechanism, something fundamental to how these transformer models work. It hints that they might be implicitly tweaking their own internal processing as they go, a kind of internal adjustment. Let's dive in.
Okay.
So let's just restate this core puzzle, make sure we're all on the same page. LLMs can pull out new patterns from prompt examples, and crucially, this works even for patterns they've likely never seen during their, massive initial training. It kind of goes against our usual intuition about learning. I like the analogy of, say, a highly trained chef. Imagine asking the chef, specialized in French cooking, to suddenly bake a completely new, maybe tropical cake they've never encountered. You don't send them back to school. You just show them a few key, maybe unfamiliar ingredients on the counter. And somehow, from just those examples, they figure it out. They adapt, create something new right there on the spot. No recipe needed. That's sort of the feeling you get with ICL and LLMs, an immediate adaptation from context.
That's a great way to put it. And historically, in machine learning, adaptation meant one thing: updating weights, optimization, gradient descent, usually. But like you said, no explicit weight updates here. So for a while, researchers have been thinking, well, maybe there's an implicit kind of update happening, something going on under the hood during inference, triggered by the prompt itself. Now, people have explored this before, sure, but often using simplified models, toy models, or making pretty strong assumptions, maybe looking only at linear layers, for instance. Those gave hints, but didn't quite nail the complexity we see in the big models.
Okay, so how does this new paper differ? What's their approach?
Well, instead of simplifying the model down, they kind of did the opposite. They abstracted a core property of the attention layers. Attention, as you know, is really central to these transformer models. They introduced this concept called a contextual block. Think of it as a generalized version of the standard transformer block.
Contextual block. Okay, how does that help explain things?
The key finding, really the core insight, is how stacking a self-attention layer with an MLP that's a multi-layer perceptron allows the block to do something clever. It allows the block to implicitly modify the weights of that MLP layer. And this modification is driven entirely by the context, the information in the prompt. So the argument is this mechanism, this way the context gets translated into what they call a low-rank weight update for the MLP. That could be the fundamental basis for ICL.
A low rank weight update.
Yeah.
Can you maybe break that down a bit?
Sure. Think of the MLP weights as a complex grid of numbers, a matrix. A rank 1 update is like the simplest, most fundamental way you can tweak that whole grid. It's not changing every number individually, but applying a sort of structured, directional change across the board. It's efficient, but impactful. So the context provides the direction for this minimal implicit tweak.
Okay, I think I'm following. So this contextual block idea, let's dig into that. What makes a layer contextual?
Right. So a typical layer just takes an input and processes it. A contextual layer, like the self-attention layer in a transformer, does that too, but it also considers the context. In an LLM, that context is the sequence of tokens, the words that came before the current one it's looking at. Self-attention, by its nature, integrates information from that preceding context. It doesn't just look at the current input in isolation.
And that's where this implicit weight change happens.
That's the core theoretical piece they demonstrate. They show mathematically that for these blocks, the effect of the piece of the context, it's equivalent to applying a specific rank 1 update to the weights of the first layer inside that block's MLP. So the output you get with the context is the same as if you'd taken the model without that context, explicitly changed the MLP weights according to their formula, and then processed the input.
Wow, okay. So the context effectively tells the block how to adjust its internal processing.
In a way, yes. It's as if the context dynamically loads the right kind of weights or the right adjustment to the weights for the task at hand described in the prompt. It's an on-the-fly configuration.
And let's be clear, this isn't the model actually overwriting its permanent weights, right? Those are fixed after training.
Correct. The stored weights aren't changed, but the functional outcome, the computation being performed, is the same as if they had been temporarily updated in this very specific low-rank way.
So it's like a temporary fine-tuning driven purely by the prompt you just gave it.
You could think of it that way, a dynamic recalibration based on the immediate context. And building on that, they connect these implicit updates to something very familiar in machine learning, gradient descent. The research shows that as the model processes a sequence of tokens in the context, the way these implicit updates accumulate step by step, it actually mimics stochastic gradient updates.
Okay, gradient descent. That's the standard way models learn during training, by taking small steps to reduce errors. So you're saying, as the LLM reads my prompt, token by token, it's doing something like tiny hidden gradient descent steps internally.
That's the analogy, yes. Each token acts a bit like a mini data point, causing a small, implicit adjustment to the MLP weights, nudging the model's internal state. It's like a micro-learning process happening live, guided by the prompt.
Without changing the fundamental model.
Without changing the stored parameters.
Yeah.
It's an adjustment to the computation being performed at that moment. And another interesting detail, they found the size of these implicit gradient updates gets smaller as the model sees more context. It diminishes and eventually seems to vanish, which is just what you'd expect from a real gradient descent process as it converges towards a solution.
That convergence behavior really strengthens the idea that something akin to learning is happening, doesn't it?
It certainly supports the interpretation, yes. It suggests it's not just random fluctuations, but a directed process.
Okay, this theory is fascinating. But theory needs proof. How did they actually test this? Did they run experiments?
They did. And the experimental setup was quite elegant. They used transformers trained on a specific controlled task, learning simple linear functions from examples given only in the prompt.
Linear functions like y equals mx plus b.
Basically, yes.
Yeah.
And they'd give the model prompts like input 2 minus output 5, input 4, output 9, what's the output for input 6? The model had to figure out the underlying linear rule just from those examples. The crucial test was then to compare two things. First, the model's prediction when given the full prompt with the examples. Second, the prediction of the same model, but this time without the prompt examples, and instead having if MLP weights manually adjusted using the exact mathematical formula derived from their theory.
So they were checking if the effect of the context was truly equivalent to that specific calculated weight update.
That was the core test.
And what did they find?
The results were remarkably consistent. The predictions, or more technically the validation losses, from both scenarios were in very close agreement. It strongly supported their claim. The context's influence could indeed be mathematically mapped onto an equivalent implicit weight update.
That's pretty strong evidence.
It is. And they also confirmed that observation about the updates decreasing over time. As more examples were added to the prompt, the magnitude of the implicit adjustments got smaller, just like a learning process converging.
Did they compare it to actual fine-tuning at all?
They did make a comparison. They noted that while the mechanism is different implicit, temporary updates versus explicit, permanent fine-tuning, both processes, seem to find similar ways to minimize the error on the task, suggesting maybe some common underlying principles of adaptation are at play. Now, one of the strengths the researchers highlight is that their analysis isn't tied to super-specific assumptions about how the self-attention layer works. Some previous theories were a bit more constrained in that regard. This work suggests the phenomenon might be more general. It hints that it's perhaps a broader property of how neural networks can kind of channel input information into changes in their effective internal structure.
That's a really interesting thought, that ICL isn't just some trick of transformers, but maybe taps into a more fundamental way networks adapt.
It opens up that possibility, yes. Makes you think about what learning can mean in these systems. But it's also crucial we talk about the limitations here. This research is still, focused. The main analysis holds rigorously for a single transformer block. Real LLMs have many, many layers stacked together.
Right, so applying it directly to a whole beef network is the next step, presumably.
That's a big open question. How these effects compose or interact across multiple layers isn't fully covered yet. And also, their analysis mainly looked at the effect of the context on the prediction for the very last token. It doesn't fully capture the whole process of generating a long response, where each new token the model generates then becomes part of the context for the next token. That iterative process is more complex.
Okay, so single block analysis focuses on the last token. These are important caveats.
They are important context for understanding where the research stands.
Understood. But even with those limitations, it feels like a significant piece of the puzzle, getting us closer to understanding these emergent abilities.
I would agree. It provides a concrete, mathematically grounded mechanism, where before we had more, perhaps, high-level hypotheses.
So thinking about our listeners, what's the key takeaway here? When you're typing a prompt and the LLM seems to just get it, what's going on?
Well, this research suggests there's this hidden dynamic happening inside. Your prompt isn't just input data, it's actively guiding the model's internal configuration for that specific interaction. It's like the context is performing a kind of real-time temporary adjustment on parts of the network, specifically the MLP weights, through that interplay with the attention mechanism.
A sort of on-the-fly tuning.
You could frame it that way, yes.
Yeah.
An implicit recalibration driven by the immediate input. And I think this really opens up fascinating perspectives on learning. It's not just the massive offline training phase. There seems to be another layer of adaptation happening constantly during use through this dynamic interplay within the architecture itself. It does make you wonder, if context can implicitly tweak weights like this. What are the boundaries? How much can be learned or adapted purely through the prompt?
A question for future research, perhaps? It definitely gives us a new lens through which to view these incredibly complex and still somewhat mysterious tools. A fascinating look under the hood. Thanks for unpacking that with us.
My pleasure. It's certainly thought-provoking work.